Okay, the last problem in this section involves doing the derivative of ln of a massive x cubed plus 4 divided by x squared fraction. So this is pretty ugly, but you know, the rule is still gonna be the same as usual. If you have ln of u and you want the derivative, then the rule is it's gonna be a fraction with u on the denominator and the u prime in the numerator. So technically I'm supposed to take all of these x cubed plus 4 divided by x squared and put them in the denominator. And when I'm finished, I'm supposed to do their derivative and put it in the numerator. Now imagine having to do that. You're going to have a fraction down here, and then its derivative is going to be a more massive fraction up there, and then you'll have to clean up this whole mess. It's going to be a nightmare to do. So instead of doing this, I'm going to take my problem and rewrite it. My hope is that when I rewrite it in a slightly different way, then the derivative will come out to be a little bit easier. And in order to do the rewriting, I'm going to remind you of a rule. So recall something called the quotient rule. So what does the quotient rule basically say? It pretty much says this. It says if you have a ln of m divided by n, then this is equal to ln of m minus ln of n. So basically, it allows you to separate the numerator from the denominator. So in other terms, if I have ln of x cubed plus 4, all divided by x squared, then according to the quotient rule, I can rewrite it. I can just remove the fraction and put ln of x cubed plus 4 minus ln of x squared. So I'm allowed to do that. And this is just rewriting the problem. I didn't do any math right here. I just rewrote it using the quotient rule. And so why would that be beneficial? Well, let's just take a look at the derivative now. What's the derivative of ln of x cubed plus 4? Well, it's got an ln, so all I have to do is grab the argument, and remember that derivatives at ln's become fractions, and the argument goes in the denominator. So the x cubed plus 4, that was in the argument, ends up in the bottom of the fraction. Now the question is, what's gonna be the numerator then? What's the derivative of x cubed plus 4? Put that on top. The derivative of x cubed is gonna be 3x squared, and the derivative of 4 is nothing. And that's it. So now there's a minus, so go ahead and write that minus in the middle. And then we have again ln of x squared. Okay, so let me use a different color. Well, what about the derivative of ln of x squared? How much will that be? Well, again, according to the rule, it's a fraction with the argument x squared on the bottom of the fraction. So there we go. Let's get started with that. Put x squared on the bottom. And then its derivative goes on top. What's the derivative of x squared? 2x. And this is pretty much the answer, except I'm going to try to reduce it a little bit and make it look prettier. The first fraction, I can't really touch it. I can't mess with it. So it's just 3x squared divided by x cubed plus 4. And the second fraction, there's an x on top, there's an x squared on the bottom. We can kind of cancel them out, and when we do, we get 2 divided by x. And that would be a perfectly acceptable way of leaving the answer here. So the benefit of doing this method is that I avoided doing a quotient rule. Remember, if I had done the derivative with the original problem, I would have to write down x cubed plus 4 divided by x squared on the bottom. Then its derivative is going to go on top. And the derivative of this is a real mess. It's going to be a quotient rule, and then I have to clean up the whole mess afterwards. So this is the reason why I decided not to do that instead. Just rewrite it and solve the problem with the rewritten version.